So what I'm going to talk about is mostly about why you should go beyond press releases and what you will find when you go beyond press releases in science, how some guidelines is how to go through proper scientific papers in scientific journals and things like that, if you haven't seen those things before. If you haven't seen them before and you don't have a science background, they can look really pretty scary. And I'm going to say, well, at one level they are pretty scary, but at another level they're not, and if you keep your head, you can kind of manage with them. But anyway, let's start. But I'm going to start with a few things which are not that. I'm going to say a few words about where science news comes from. And I'm mainly talking here about science news in the mainstream media. And in the UK, though things are pretty similar in North America and in several other parts of the world. So this is, science is an activity where people have to cooperate. It's very cooperative. So scientists have to find out what other scientists are doing. And there's a whole range of ways in which they do this. They can read articles in scientific journals, which is mostly what I'm going to talk about. They can read preprints, which are sort of preliminary versions of articles that they hope will end up in scientific journals. I could say more about that at the end in the Q&A if you want. They go to conferences, they go to scientific meetings, they go to seminars, there are mailing lists that get sent around, there are specialist websites for particular science areas, there are blogs, there's all sorts of stuff. They talk to their contacts, obviously, other scientists who they work with, there's gossip, but they also use what you might call standard mainstream media to find out about things. So that's what scientists do. Where do journalists learn about what scientists are doing? Well, exactly the same, except to a large extent, in terms of what happens in the mainstream media, they learn about it through press releases. There's an amazing flood of press releases. There's more reliance, various content analyses have shown, on media releases in science journalism than in most other areas of journalism, if not all. Now, why is this? There's a lot of reasons. One is it's the only way that non-specialist media can keep up, because there's a phenomenal flow of this stuff. 2.5 million scientific articles a year appear, new ones, 7,000 each day. There are 28,000 different scholarly peer-reviewed journals in English, and this is in 2015. It's gone up since then, doubtless. On Eurekalert, which is this US site that accumulates press releases, and you can look on there are 200 a day. And if you're working in some areas of science journalism, we might have to deal with 60 or 70 of these in a day. Scientists and research organizations are all shouting louder and louder because they've got to make their voice heard through all this noise. And the louder they shout, the worse the position gets. So that's my take on why this happens. And another thing I'd like you to remember is that it's a very long way from research to what readers can find out. The scientist does the research. There's a lot of stuff before this about how they get funding, how they decide to do the research. They produce an output, a paper, a talk, and a conference, whatever it is. Most of those aren't press released. Most of those aren't terribly interesting to the public, even if they were press released, so they're not press released. Some are. Someone has to decide to make the press release. That's someone at the university or research center or journal. Then that goes to journalists who decide to write a story about it or not. Then somebody else writes the headline, and eventually, which persuades people to read it, it eventually goes to the reader. All these people have different interests, different motivations, and it's a complicated business. I mean, it's no different with other types of journalism, but sometimes it looks as if it's different. Anyway, that's that. So, why do we need to go beyond press releases? Well, this is an investigative journalism summer school. Why would you stop at the press release? Surely it's not the work of a journalist to just regurgitate press releases that someone else has written. So that's in a sense the reason why you need to go beyond the press releases. I should have said at the beginning, if anybody wants to ask anything, just shout out, and you will have to shout out since you're all hidden behind these things. So if I say something you don't like, you don't understand, just ask. I hope I leave room for Q&A at the end. Anyway. When to go beyond press releases. This is what press releases look like. You're bound to have seen press releases. I'm talking about some of these later. But anyway, they're press releases. Here are just some suggestions of why and when it's important to go beyond the press release. My view would be that you should always go beyond the press release. Even if you're writing a story in a big hurry, you should at least have a quick look at the beginning of the science paper it's based on, just, to make sure there's nothing really mysterious. First point about exaggerations. Can I make this work? Does this? There. Oh, that's a bit crap, isn't it? Exaggerations in press releases do happen. The people who write the press release, they're PR people. They're trying to persuade you that you should go to their university, give their charity more money, whatever it is. And so there's exaggeration. There's a lot of research being done. It's a kind of niche area of research by psychologists in particular about what sort of exaggerations happen. So they happen a lot. These are people you can check with. Again, I've got a bit more about this later. You can check with the Science Media Center or the equivalent in other countries. You check with the author, you check with the paper in particular, and you can also check with sort of tame scientists who you happen to know, or statisticians or whatever. Now, here are just some reasons, and again, I'll say more about these, for smelling a rat about a press release. Many press releases, much science journalism is about health and medicine. Huge predominance of that. So I suppose next would come the environment and lots of areas of science. I mean, when do you read physics news unless you read in specialist journals or they've discovered the Higgs boson? Hardly ever, which is a pity, but that's the way it is. So a lot of these are to do with health, and I'm talking about health quite a lot. If they give health advice, somebody did some research, and that means you should all stop drinking coffee or start drinking coffee. At least check that out. That is exaggerated a lot. If they say something causes something, I'll explain why. You may need to be skeptical about that. If there's something that we did something on 10 rats and that tells us what has to happen to humans, that's awkward. If there's something which talks about statistical significance, and this is about the most technical thing I'll talk about later, that can be an issue. And then the things which I'll talk about later, things which haven't been controlled for in the research. If it's been done on a particular niche group of people that live on some obscure Pacific island, it probably applies very well to them and not necessarily elsewhere. If the research hasn't been peer-reviewed by scientific peers, and that would be the case if it's a preprint, for example, or often if it's a conference paper, and a recent content analysis and study of press releases said these are the things which are in papers and often omitted from the press release. Anyway, what's often omitted from the press releases, and may be important for the story, is limitations of the study, what didn't it show, and then who funded it, and are there conflicts of interest. There's a very good feature in Nature, the science journal feature by Tom Chivers that came out day before yesterday, to do with conflicts of interest in psychology. And that is not really based on what was in the papers because it's about people not declaring interest. But it's an important area. There are lots of stories, in my view, in that, which aren't really science stories, but they're important stories anyway. Okay, so that's reasons when to go beyond the press release. Now, if you read the paper, the trouble is it takes time. They're quite long. They're not like a page, like a press release. But they've got a typical structure, so you don't need to read the whole thing. Whoops, I pressed the wrong button. They have an abstract at the beginning, which is a summary, and it tends to be very abbreviated, but it also tends to be something that it tells you everything you need to know, probably, if you can make sense of it. The title these days, particularly if it's in a medical journal, tends to be very standardized, and it says what they did, and it just says what they did, and it's very clear. But if you go to more obscure journals in some other areas of science and things like that, you may find that it's as bad as the worst news headlines. It says stuff which is not in the paper. It exaggerates, so you've got to be careful with the title. Then the bit which comes right at the end of the paper is the discussion section. That says what they think they found, essentially, and very often it has a section on strengths and limitations of the study. The limitations bit, I think, is particularly important because the reviewers, if it's been peer-reviewed, will tell them, you must say what you haven't found in that section. And so often you will read a limitation in there which is really important, isn't in the press release, and you need to know about. And then there may be an introduction which puts it in context, because the trouble with science press releases about papers is they're about the last piece of research that was done. They're not about the whole context into which this fits. Usually they don't make sense unless you look at the context. and the introduction will tell you at least what the scientists who wrote the paper think the context was. Now, if it's in a medical journal, lots of them have sections, they've got kind of different names, what's already known on this topic and what this study adds. They are amazingly useful. They're actually written for medics, doctors, who need to use this stuff to decide how to change how they're dealing with their patients. They haven't got time to read all this stuff either, but it says, we knew this, and we've added this bit. That's what the research really did, not what the press release says it did. Now, these come in a particular order. I mean, there are other things. There are the methods section, and I'll give a reason why that might be useful later, and the results, which give all the results in detail, enormous, great long tables, and to be honest, the important ones are nearly always in the abstract, but you might want to look at those anyway. And they come in a particular order: title, abstract, introduction, methods, results, discussion, apart from the ones that don't. Some annoying ones decide no one cares about the methods they used, so we'll put it in a sort of appendix at the end in small print. And they drive me mad, but that happens. Okay, so here's a few of the kind of headlines. This is just some examples of the sort of thing you've seen that might come up from this sort of research. I won't talk about all of these. Can't imagine why I put them there. Right, so the technical bit. This is the statistics bit. I'm a statistician, so I have to do this. Comes with a job. Statistical significance and p-values. I should have asked, how many of you got a science background, have sort of studied science at university or I know you have.
Not to degree level.
But yeah, so some have and some haven't, which is fine, because that means you may know some of this if you've studied it. You may know some of it wrongly if you studied this, because some of this is often taught wrongly, but that's another point of view. Statistical significance is a really awkward concept. It sounds nice. I mean, you know what significance means, importance and all that. I mean, you know, that's what the word means. It doesn't quite mean that. Statistical significance doesn't mean what you possibly at least thought it means. It's nothing directly to do with importance in the real world. So there can be things which are statistically significant that have absolutely no importance to anyone, even probably the scientists who did the research. And there can be other things which aren't statistically significant. They may not be true, but if they are, they're really important. It's a way of judging whether some finding can be explained away simply by chance variability. So the reason the patients we gave this new drug to were more likely to get better is simply because the way the thing worked out, they happened to be the people who were going to get better anyway. Right. There's been a huge degree of criticism of statistical significance and the way it's used in the past 5 or 10 years in certain parts of the science literature. The way they are used is changing, but it hasn't changed that much. It depends which area you're working in. If you're looking at papers in clinical medicine or in psychology, people will get all excited about this and do things in different ways. If you're looking at research in chemistry, if it's got this kind of thing in, or a lot of biological areas, people just do the worst examples of what I'm talking about here. Anyway, it's usually based on a number called the p-value, and these are really quite awkward to understand. So what is one? If you've come up on these before, it almost certainly doesn't mean at least what you originally thought it meant before you were sort of better trained. It's a number. It's a number between 0 and 1, or between 0 and 100%. And the trouble is, it's a kind of backward scale. The smaller it is, the less likely it is that a finding is just chance, sort of, more or less. And there's a common convention that if it's less than 0.05, which is 5%, a result is said to be statistically significant. But that, I must point out, is only a convention, and it doesn't actually apply very well with big data, because you can get things which are statistically significant in big data and are so small that no one should care about them. No one does care about them. So here's an example. This isn't the sort of technical wording people would use, but there might be something in the summary of paper. There's people, you know, they're comparing two drugs. People on the new drug had on average lower pressure than people on the old drug. P equals 0.03. So that's less than 0.05. So it's statistically significant. Now, what you think that might mean is that there's just a 3% probability that the result was due to chance. But it doesn't mean that. It also doesn't mean that there's a 100% minus 3%, 97% probability that it wasn't due to chance. You might think it means that. That is absolutely not correct. It does mean the following complicated thing. And what I suggest you remember is that it doesn't mean these things, probably more than what it actually does mean, because that's complicated. What you do is you assume the new drug has the same average effect on blood pressure as the old drug, right? And then there's a 3% probability that a difference at least as extreme as what happened in the experiment would happen. So it's a hypothetical thing, and then it says under certain hypothetical circumstances, there'd only be a 3% chance of this thing happening. Well, you might say, well, I don't want to know that. I want to know what the probability as a result was due to chance. And the trouble is, you can't say from that information. And in many circumstances, you just can't say full stop. There's various research on what these things might actually mean in the real world. There's a famous paper that says, by John Ioannidis, that says half of the studies which found a statistically significant result, actually it's phony. They're false positives. Now, you can check his calculations, and some of them are a bit dubious, but the point is, what he's saying is, it's not 3%, it's not 97%. Those have technical meanings, and they're not quite what you think they are. However, that doesn't mean it doesn't matter. I'd say it does matter. First of all, suppose the p-value is too big, suppose it's bigger than this 5% thing, and it remains plausible that there's no effect, that it's just chance variation, that with the blood pressure thing, if it had been bigger than 5%, the people who were on the new drug just happened to be the ones whose blood pressure was going to improve anyway. But the trouble is, that doesn't mean that it is just chance variation. It just means that it might be just chance variation, and you don't know the probability that it is. Now, here's another point. Supposing a treatment or whatever you're looking at has absolutely no effect, there's a 5% chance, because of the way these things are constructed, that every statistical test you do will report a significant effect. So that's fine if you do 1, that's not very likely. But suppose you do 20, 5%'s 1 in 20. You would expect that even if there's nothing going on, one of them would come up. And so people might do 100 tests sometimes in a paper. And it's really bad if they just don't make adjustments for the fact they've done lots of tests. There's statistical methods for doing that. And it's like having a lot of shots at a goal. If you have a lot of shots at a goal, the chance that one of them will go in, even if you're useless at football, goes up. And so there's a risk of what's called data dredging, just chugging through all the data you have until you find something that's significant. There are lots of methods to correct for the multiple testing and so on. And doing this kind of thing is a form of what's called p-hacking, which is fiddling around with what you're doing in order to get a statistically significant result. And that happens much more than you would think, and it's kind of awkward. So one alternative approach to this uses what are called confidence intervals. Technically, they're linked to p-values in a complicated way. But what it gives you is a range of plausible values for something that the study measured. And they're kind of more useful, and I'll give an example. I'll show you an example of those later on. Is this making sense of some sort? Just be careful. That's the message on this. So here's an example. This is a paper from a couple of years ago about air pollution in stillbirths. And these are the headlines. Air pollution could increase stillbirth risk. And, pregnant women should consider moving to the countryside. You recognize the layout, probably that's from the Daily Mail, because air pollution may raise the risk of stillbirth, and then there's a lot of detail. And the scientists did actually say this in the paper. Now, what they were doing here was something called a review, a systematic review, and meta-analysis. Meta-analysis, there'll be a little bit more on that later. It's a statistical way of putting together the results of different studies. And it involved 13 studies, so in fact, most of the results depended only on 3 of them, or only on 2 of them. So it looks as if it's good. They looked at 13 different studies across the world, but actually, for good reasons, 10 or 11 weren't telling them anything very useful. Now, the paper abstract says very clearly, although not reaching statistical significance. But they did say they were all elevated anyway, these risk things. Now, the press release did mention a few caveats, a few things you ought to be careful about in interpreting this, but it didn't mention the lack of statistical significance. It said they're suggestive findings. The press release gave the relative risk for just one pollutant, and it's not clear how big that risk is anyway. I'll say a bit more about that in a minute. And for later, all of this is based on observational studies, so actually you can't conclude for sure that it's the pollution that causes the stillbirths. It's just correlated with the stillbirths. So this is the really scary looking bit of the abstract which talks about the results. 13 studies met the inclusion criteria, although not reaching statistical significance. All the summary estimates were elevated, and then there's a whole bunch of numbers for exposure to different pollutants. So there's, you might have, if you didn't know about these, you'd have to look up nitrogen oxide, is that nitrous or nitric? Nitrous. Carbon monoxide, sulfur dioxide, little particulates, and bigger particulates. So you might have to look that up. But what's all this stuff? And then there's a bit more detail. Just concentrating on the one about PM2.5, which is the very tiny particulates and get right down inside your lungs and are thought to do a lot of harm. What they worked out was the effect of comparing people, one of whom had 4 on the scale for measuring this thing, more than the other lot on this. So that's what the 4 is, and those are the units. And you might have to look that up. And then there are these annoying abbreviations. EE means estimated effect. It says that somewhere in the paper, but you might miss it. And on what scale is it an estimated effect? 1.021. And what they're saying is, if this stuff had no effect, then comparing people who had a certain level with people who had level 4 higher, what they're doing is comparing those two, and they're dividing one by the other. And if those two were the same, that would be exactly 1. So they're saying it's not 1, it's 1.02. That's 2% higher than 1. So it's a bit of a difference, but it's not very big. Now remember I mentioned these confidence intervals. They said with a 95% confidence, which means something complicated, the interval for that thing goes from 0.996 to 1.046. That is actually the stillbirth rate in people that had the higher pollution could have been lower. It could have been slightly lower. That's plausible given the data. Or it could have been nearly 5% higher. So there's uncertainty, but whatever it is, the effect is very small.
This is what I call a hostile study, because the only thing it does is terrify pregnant women who can't move.
Absolutely, absolutely. Well, except, they can move to the country. You get pregnant, first thing to do, move out to the city. Forget everything else. And then the other thing is, what's this n equals 2? When it says n, it means a number of something, but it's really not clear what it's a number of. What it means is 2 of the 13 studies. The press release mentioned, as I said, only the business about PM2.5, and it did talk about 2%. This could be due to chance. The point being that these women lived where they happened to live. They were not told you must go and live in a high pollution area or a low pollution area. Maybe it's just the sort of women who lived in the areas where the pollution was higher are more likely to have stillbirths for some other reason. I'll say more about that aspect later, but I really think this is quite dubious. Anyway.
This was written by men, wasn't it?
No, there were women involved too. I don't know who was the team leader. These are the messages I'd like you to take away about these things. Statistical significance is a way of judging whether some finding can be explained away by chance variability. It can be dodgy. And there's this thing which I said before about what the thing means. If you calculate a lot of them, that increases the chance of finding false positive results, and it's often better to use confidence intervals. So any questions about that part? No? Good. Hope you haven't all gone to sleep in the heat. Right, I'm now going to talk about different types of biomedical study. And this is mostly about biomedicine, but what I'm going to say applies in other areas of science as well. And to understand this is important because it determines the strength of the findings and the confidence, not confidence interval, confidence that you should have in the results. So here are just, people put these things in order. This is a bit dodgy, to be honest. I'm going to talk about some of these, but not all. The best kind of study in medicine is a randomized controlled trial, and I'll say why in a minute. Or even better, a good systematic review of a lot of RCTs, as they're called. But then there's a whole bunch of other things that, jargon in the paper will say this stuff, and so you need to have some clue or be able to look at what these mean. And eventually you get to animal studies, which don't really fit on the same scale because they're looking at different things. And there are other kinds which I've missed off this list. But the important thing I want you to bear in mind is all these ones in red, which is most of them, are what are called observational studies. That is, they're not experiments in the purest sense. That is, you haven't manipulated what was done to some people. You've just gone out and observed what happened with the people. And that makes a difference to what you can conclude about them. So here are just some headlines. This is from a 2-month, or was it 3-month period, a bit more than a year ago. These are headlines from different things. These all come from a different type of study on that list. And later on, I'm going to ask you to guess what some of them are. And you will get this wrong. But don't worry. The trouble is that if you just read the press release will have that. It'll have a bit more information, but it might not give you the information about exactly what kind of study it is. If it's a good press release, it will, but they aren't all good. Okay, so first of all, what's a randomized controlled trial? Well, RCT. Let's take the three letters in reverse order. T, it's a trial. It's trying out something, some new treatment, some new intervention to try and make people better. C can mean controlled, or it's sometimes taken to mean clinical. Clinical means it's being done on ill people, patients. But control means there's a basis for comparison. That is, you don't just give everyone the new drug or the new type of surgery, whatever it is. There are some people who are given an existing treatment or no treatment at all or something like that. It all depends what comparison you want to make. And that's important because you've got the people who differ only in terms of the treatment they were given. Was it the new stuff or the old stuff? Random means that the people who get the new treatment or the old treatment are chosen at random. Now that kind of sounds at one level crazy. Why choose them at random? Why not just say, oh, this one's more suitable for the new treatment, this one's more suitable for the old treatment? It's essentially to avoid, there are 2 reasons. One is to avoid bias. Actually, there are 3 reasons, but the third one's technical. In that, the doctors who are running this trial might unconsciously or even consciously decide to give the new treatment to the patients who are going to get better anyway, or the new treatment to the patients who aren't going to get better anyway, and that'll bias the results. There's also what's called blinding, which is that it's so easy to influence patients with many treatments. If the patients know which treatment they're getting, all the people who are evaluating the results know what treatment they're getting. That can really mess stuff up and cause other biases. So it's another reason for doing these things in a blind way, as it's called. So that's why it's done that way. And it's a very firm way of producing evidence that some treatment works, because you have people which are essentially the same apart from whether they were randomized to get one treatment or another. There are fancier ways of doing this, but I'll just talk about the simplest way. And if the only difference is that some of them got a new treatment, some of them got the old treatment, and the people on the new treatment do better than the people on the old treatment, then what else could it be apart from the difference between the treatments? You still need to do the statistical tests and so on, but essentially that's what's going on. So if it's done properly, it's really strong. But I said systematic reviews are better than a single one. Why is that? The answer is, well, there's more data. Somebody's done the trial in London, somebody's done a trial in Beijing, somebody's done a trial somewhere else. So there are just more numbers. Also, usually because they've been done in different populations of people, there are more settings. And it could be that maybe this thing works well with the population of London, it doesn't work well with the population of Beijing. And if you do a review, you will find that out. And that's important to know if it works different. In other words, you can look for heterogeneity, differences between the way things work in different things. And there's a statistical approach to putting the data together, which is called meta-analysis. And I could say more about that later if anybody wants to know. It can be quite technical, but you will see loads of papers on this if you work on medical stuff, because they're done all the time. Well, what about statistical analysis of this? Well, I mentioned the possibility of doing a lot of statistical tests, some of which will be significant even if there's no real effect. So there's a possibility of cheating. You say, well, I'm going to measure 50 things on these patients, and then I'll report the one that they haven't get better on. But with RCTs, they have to be registered in advance, or they won't get published in a good journal, saying what they're looking for. And then if you can go back and look at what they registered, you can check whether they did what they were going to do. So almost always they do what they said they were going to do, otherwise they'd be caught out. But they can do things which aren't registered. Something interesting happens. They say, well, the primary thing I'm looking at is this, secondary thing I'm looking at is this other thing. But hey, we happen to notice that this was going on. And they can do statistical analyses, but they start coming upon the possibility of cheating or the possibility of looking at it properly. And the press release hardly ever is clear about that, but the paper will make it clear. And you could always look at the registration if you really want to check up. Okay, so now I'm going to go on to these observational studies that I mentioned. Well, first, any questions about randomized trials? No. I mean, they're relatively simple conceptually. Bloody difficult to do, and they take ages and are very expensive, but hey. So the general idea in epidemiology is the study of the causes of diseases and risks of diseases and things like that in populations. So it sounds as if it means epidemics. It doesn't necessarily. They're just part of it. So the idea in epidemiology is you might not be able to do an RCT. If you want to find out whether breathing polluted air is bad for you, you can't choose people at random and say, right, you've got to go and live in a polluted area for the next 10 years and have lots of babies. And you're not allowed to move to a polluted area, even that's where your job is. I mean, it clearly can't be done. So that's the problem. But the idea is that there's an exposure to something which might be a risk, or it actually might reduce the risk. And there's an outcome, which be you get a disease, you die early, whatever it might be. And what you want to know is whether the exposure changes the chance of the outcome, right? But all you can do is observe what people did. You can't do this experimental thing of saying you will take the new drug, you will take the old one. So they're observational studies, and there are many types of these. I won't go through the detail. This is on the handout. Cohort studies, so let's say the exposure is drinking coffee and the risk is whether you get gout. People have studied this. Actually, they found results that go in both directions. Some found coffee increases the risk, some found coffee reduces the risk. You take your pick. But anyway, you could do that. So you choose some group of people that happens to include some people who drink coffee and some people who don't. That's the cohort. You then follow them up for a long time, if it's a prospective study, and find out whether they get gout. That can be expensive, take a very long time, and it has various snags. And if not many, it just doesn't apply to gout, which is actually relatively common. But if you're looking at rare disease, you have to follow up thousands and thousands to get a few people who got the disease. Really expensive. There can be retrospective cohort studies, which means you come back in a lot of years and you have somehow got a record of who used to drink coffee, and then you look and see whether they got gout. But the point is, people are chosen on the basis of the exposure to the risk. But there are also things called case control studies, and the point about these is these work for rare conditions as well as common ones. You find some people who've got gout, and you find some other people who are similar, and a lot hidden in what might be meant by similar, who haven't got gout, and then you look back into their history to find out whether they drank coffee a long time ago. And there's all sorts of problems about actually getting that history. So these are considered to provide slightly worse information than the other sort. And this is just a bit more about meta-analysis. Because you can apply meta-analysis, it's very often applied to these epidemiological studies. And as I've said, not all meta-analyses are good science. There are lots of things. If you put together a lot of rubbish studies, you'll get a rubbish outcome. And there are problems of putting together studies with different levels of evidence. Putting together a randomized trial with an observational study, that doesn't really work. And there's an issue about what actually gets published and what you can find, because much research just doesn't get published. So let's look at another example, pollution. Sorry, I'm forgetting where I am. These are the headlines we had before. Now, one of these is a randomized controlled trial. One of these is an animal experiment, and the others are all observational studies of different sorts. So anyone like to suggest which one might be the RCT? I mean, you can't tell from a headline. Probably the last one. That is, people often say the last one, and I think that's reasonable. Except you'd have to be taking the paracetamol for something else if the thought is it's going to affect your daughter's fertility, because that's a harm. So it probably isn't the last one, but you're not the first person to say that. It sounds like you could do it with an experiment, and we'll come back to that later. It's actually the first one.
No, that was the one I was
And this is kind of odd, because what the trial was they got various people, they were, if I remember rightly, men who were getting on in years, so probably could have been me. And they got them to go for walks. And they got them to go for walks either along Oxford Street in London, which, if you don't know, is lots of traffic and horrible levels of traffic-based pollution, or Hyde Park, which is a nice park nearby. And not the best air, but it's much better than there. And then they measured various things on them later on. And they thought that this exposure to potential pollutants wasn't bad because they probably went for a walk there anyway. And so that was sort of okay. They did do a randomized control trial on something that might be bad for you. I said that doesn't happen, but it did happen in this case. It was considered ethically acceptable. And they essentially found out what it says. I mean, this is a good headline. Going for a walk's good for you, but if you go for a walk along Oxford Street, you might as well not have bothered. That's what it said. So which one do you think's the animal experiment? Go on, be bold. Spinach. No, it's that one. Because this was actually pregnant, I've now forgotten whether they were mice or rats.
They have no other reason to take paracetamol.
No, they have, well, I don't know, you want to be careful to your lab rats. When they've got a headache, they will, no, they won't tell you. And they looked at the fertility of, I mean, it's very difficult to do this sort of research because it goes across generations in humans, but with rats or mice, they got a short time between generations, so you can do it. But the whole thing was written up as if this was telling you about humans, and whether the physiology of paracetamol works in anything like the same way in rodents as it does in people is an interesting question, probably not. Anyway, all the others are various sorts of observational study, and so they have various issues to do with that, which I shall come to. But the point about this is, it's important to know what the study type is, because that tells you how much evidence there was, and there's a bit of detail about that. If you get a bad press release, it won't tell you, and this is dead easy to check up in the papers because they're very clear on this. Right, absolute risk, relative risk, and so on. What am I talking about here? Well, let's say, again, you're thinking of one of these epidemiology things, coffee and gout, and what you want to know is, typically, how likely are you to get gout if you drink coffee? And is that a big number? That is it different from what happens if you don't drink coffee? And how do those two things compare? That's what you'd ideally like to know. You'd ideally like to know all those things. But you don't always know all these things. This is a good example of a study where you could know all these things. It was a study on whether taking vitamin D reduced the risk of acute respiratory tract infections, which is colds and flu, essentially, things like that. And this was a way which was not in the paper, but it was in the supplementary material for the paper to demonstrate this. It's what's called a Cates chart. And what happens is there's 100 of these little faces, and the green smiley ones aren't going to get a cold anyway. The red ones are going to get a cold whether they take the vitamin D or not. And the yellow ones are the ones who would get a cold if they didn't take vitamin D, but if they do take it, they won't take vitamin D. And you see that gets all the numbers across in a nice graphical way. That's very nice. But if you want to get across in words, it's kind of harder and more awkward. But let's just see what they would actually do with this. The first point is all those numbers you need to know aren't always in the research paper, and there are good statistical reasons for that. And the scientists don't care because they know what the context is. What they might give you instead is what's called the relative risk, or the risk ratio. That's the percent that got ill that were exposed divided by the percent that were ill that weren't exposed. So the vitamin D study, you're exposed to vitamin D, it's good for you. 39 out of 100 were going to get it if they got vitamin D, and 42 were going to get it if they didn't get vitamin D. And you divide one by the other, you get something which is a bit less than one. And you could say 7% reduction in risk by taking vitamin D. And in fact, that's sort of what the paper did say. But the trouble is, it's difficult to make sense of that, because unless you know how common it is to get a cold, which it's a cold, people know how common it is to get a cold, it's pretty common. But suppose it's some other disease. So saying it's 7% less or 2% more something, it really isn't terribly helpful. Now, the paper may give the relative risk. It may give even more complicated things called odds ratios or hazard ratios. And I haven't got time to talk about what they are, but the point is they're also relative measures. They're relative measures. And they're not very useful necessarily in writing up a story. You need to ask the scientists to give you useful numbers. Because I and many other people have been nagging press officers to get these numbers out to scientists to begin with, press officers have started nagging the scientists to give them. And often you will get, or sometimes, you'll get a press release which has got good absolute risks, good other numbers in, which aren't in the paper because the press officers made the scientists tell them. If that doesn't happen, ask them. We haven't got time for this, and it's dull anyway. But why absolute risk matters is that the impact of a new treatment depends on the absolute risks. It depends on how many people are going to get this disease. And if the baseline risk, if the chance of getting this condition is very small, then doubling or halving that risk might not actually be very important. But the thing is, if you're the person who's got the condition, it's important to you. And this is where we get interesting contrasts between what's important in a whole population and what's important to a few individuals. And scientists have enough problems like that, but if you're writing this up for the general public, that's even harder to deal with. But basically, I would suggest you need to know what the absolute risk is so that you can write up the story properly. Does that make sense? But just to check you haven't fallen asleep, and I wouldn't blame you in this heat, here's a quiz. A dietary supplement reduced the risk of having at least one cold in a year by 20%, according to an RCT. So it's good evidence. You don't have to worry about what it means. And in a given year, people who don't take the supplement, this is known, let's say, have a 50% chance of getting a cold. So a large group of people take the supplement, and what I'd like you to think about is what's their chance of having at least one cold the next year. Reduction by 20%. Right. So have a think about it for a take. It's, right, anybody vote for 30%? No, but it kind of, it's this awkward thing about percents. Reduction by 20%, does that mean 20% of the 50%? In other words, a fifth of the 50%, that's probably what it means, but I didn't say that. It might mean knock off 20%. You can't tell. Why might it be 44%? Because sometimes that's what the odds ratio is. If people work with odds, which they do for good statistical reasons, odds are like betting odds, it actually comes out to 44%. But actually, does anybody give the answer D? D is correct, in my view. You know, yeah, it's good to be numerate, and the one piece of mathematics, if it's mathematics, that I would suggest every journalist should know about, whatever field they're working in, is percentages. But actually, you can't always tell what they did. Actually, that vitamin D paper worked in odds, and it said some very confusing things because of that. So if the paper only reports relative measures, ask the researchers. They might be in the paper, but whether you can find them is another matter. The papers are technical and complicated. Press them for an answer. It all takes time, but you should press them for an answer. So here are just a few messages about that. The impression you get from a story depends on whether you report the relative risk or the absolute risk. And so you can slant what you write. Actually, it's sometimes really difficult to avoid slanting what you write, or you can be taken in by these comparisons. And they can be difficult to get. So is this the last? This is almost the last thing. Confounders and causality. Here's another study, and it's again about pollution being bad for you. Traffic pollution putting unborn babies' health at risk. It's really bad for unborn babies, and could even be pensioners as well, which is me, so I'm worried about this. And this is based on a study from a couple of years ago on air pollution, traffic noise, and birth weight. It was a cohort study, observational, but really big, 540,000 births, and they recorded air pollution and traffic noise at the places where the mothers lived. That was the exposure, and the outcome was birth weight. How heavy were the babies when they were born? And what they found was there was a higher chance of low birth weight for mothers in areas where the air pollution was higher. The odds went up by 2 to 6%. It's not a huge effect, but they found it. It was statistically significant, if I remember right. And there wasn't an effect of traffic noise. Now, the point is, if this was a randomized controlled trial, you'd have allocated mothers to go and live in areas of low and high pollution. But obviously, you couldn't do that. It was observational. And maybe the mothers who lived in polluted areas also smoked more tobacco, or they were older, or something like that. You know, things that are also already known to have an effect on birth weight. Things which might mess stuff up like that are called confounders in the jargon. The press release said the findings held true after other potentially influential factors were taken into account, such as those things. But the question is this enough to avoid this potential confounding? And you can't really tell. Reading through the paper, though, might give you more of a clue, because they may mention things that they'd like to control for statistically, but they couldn't. Or it might just make you think of something, then you go and ask them if it matters. The trouble is, it's really difficult to read in the paper. This is what this one said about the confounders, and there's a lot of jargon there. So somebody was going to ask something. No? An interesting thing is that they adjusted for some of these things at census output area level. And they say that's fine because other people have done it before. And so, in other words, they're saying, we don't know how much people smoked. We don't know how economically deprived they were, but we know what their neighbors were like, so we'll just give an overall thing in terms of their neighbors. And maybe that's a bit dodgy. But the point about this is because of potential confounding, you can infer causal effects from a RCT because you know there aren't any important differences. You can't from an observational study. Statisticians say correlation is not causation, but we're not always good at saying what causation is. And so the thing I was asked at this point is, well, how do we know smoking causes lung cancer? So, smoking causes lung cancer, yeah, everyone knows that. Information for that comes from observational studies and animal studies, because there have been no randomized controlled trials making people smoke for decades. And these things are things where it's awkward to know what causes what. And what's actually going on is a picture is built together from different bits of research. It's sometimes called a causal narrative of how everything works, and there are various ways of doing this. At some point, the balance tips over to people believing that what's going on is really causal. And if you read the discussion section of the papers, they will give reasons why they think it's probably causal, and also, if they're good, reasons why it might not be causal. And they do say that kind of stuff, and that's kind of good, but it won't be in the press release. So this press release said this is an observational study, so no firm conclusions to be drawn about cause and effect. The BMJ and other journals usually do say that, but not everyone's so careful, so be careful. Now, with confounders, you can make statistical adjustments for confounders that you know about, and they usually do. They will write a whole lot of stuff about this. Press releases won't tell you which, and you might smell a rat from that. If you can think of what looks like an important confounder that isn't mentioned, you might be right, it might be important. Ask the researchers whether they thought it was important. And I won't cover that, it's in the handout. Right. Okay, so here are the messages. Confounders can muddy the waters in observational studies. Don't make causal claims from observational studies, or at least be careful. And be careful about writing them up, even if the researchers make the claims. And that's important. So have I got time for any of this? I think I've got time for one of them. This is what annoys me in stories about research, and I'll just do one, because this goes to association versus causation, relative and absolute risk, and statistical significance. So this is a headline from a couple of weeks ago, 20th of June. Fears cleaning fluids can cause autism risk to unborn babies, blah, 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 blah. That's in the Daily Mail, and here's another one, which is in the online version of the Daily Mail, which is written by different people. Exposure to solvent chemicals makes it more likely you'll have a child with autism. Well, as you might guess, it's an observational study, so there are all sorts of awkwardness about cause. This is the press release, and I wanted to point this out for two reasons. One is, it has this stuff at the top. Peer-reviewed, yes, evidence type, observational, subjects, people. There is a campaign. Putting these headings on press releases happens in the UK a lot. They were introduced by the Academy for Medical Sciences as a result of a critical report about how stuff was being got across. So you can find out if it's been peer-reviewed, you can find out if it's observational, and you can find out whether it was done on people or mice. Okay, that's good if they're in. And it does say some useful things. Cautious interpretation is needed. And here's a bit more, it's my emphasis, and there's a few details. The 1.5 times more likely is mentioned there. And they do say it's observational, but then we get this last sentence, only a few parents, after correcting for statistical bias, the observed associations no longer remain significant. So it's not even statistically significant. Now, the Science Media Center has this service called Before the Headlines, where they get statisticians anonymously to comment on these things, and they tore it apart. It's observational, so it can't establish cause. It's full of multiple statistical tests, and these statisticians, it wasn't me, worked out that the way the study was designed, it will generate a false positive about 50% of the time. Because they looked at umpteen different potential pollutants, and solvents were the only ones that were positive. None of the other ones were. And that might be random. They said it's a rare condition. They said, well, look, this is really quite weird because the mothers who had moderate exposure to solvents had a bigger relative risk than the ones who had high exposure. How on earth does that work? And there's various other dodgy things about it. Were all these cautions reported? Well, they didn't get into the Mail stories. There was one external comment in the Ben Spencer story, but it doesn't really say very much, except this guy at Leeds said there should be other things. But the good point here is the Science Media Center really put its boot into this study. It didn't get reported in any other dailies. Dodgy study, therefore, getting comments from scientists, which will allow you to say to your editor, this is rubbish, we shouldn't be doing it, can help.